Okay, so for concave mirrors, the object can be in three different locations. It can be outside the focal point. It can be at the focal point. Or no, inside the focal point. Let me see. I forget what order I do it. I'll do inside focal point and at the focal point. All right, so we're dealing with concave mirrors. That's this one. Now this one where y'all all look upside down, are you inside or outside the focal point? Which are you? Inside or outside the focal point? You're outside, right? The focal point's right about here, and you're at a distance further from the focal point. That's what I mean. And if you're inside the focal point, then you look a lot different than you do now. How do you look if you're inside the focal point? Upright and big, right? Like a makeup mirror. But right now you're outside the focal point, and you look inverted and smaller than you actually are. So outside the focal point, I can draw my three rays. Ray number one, parallel to the axis, and through the focal point. Ray number two, through the focal point, and parallel to the axis. All right, so now I have enough rays to draw where my image is. My image, then, is going to be right here, and it's going to look like this. That where my rays originate and where they cross give me the same place on the image. Right now, if I draw rays from the nose, I would get rays crossed right here. If I draw rays from the mouth, I would get rays that cross right here. Okay? So wherever my rays cross and where they originate, they give the same part of the image. They start up here, so they give up here. That means that my image is going to be inverted. We'll see upright images. Upright images, the rays will cross above the optical axis. We call this the optical axis. Where they cross give me where the image is. This was ray number one. This was ray number two. Or excuse me, I got that switched. No, that's right. Ray number one, ray number two. Hey, Hillary. Ray number three, which is through the center of curvature. Oh, let's see. Shoot, I got this a little off. I'm going to fudge this a little bit. I'm just going to say my center of curvature is over here. I just didn't draw them with a straight edge. But through my center of curvature, it'll go like that, and then it'll come back again. If you draw it with a ruler, if you're very careful, and some of you might have done this better, it will, if I draw a ray through the center of curvature, it'll come back, and it'll cross where these two rays are. Okay? And then fourth, I can draw a ray to the center of the mirror, right here, and then follow the law of reflection so that these two angles are equal, and they'll cross all in the same point. So this is ray number 4, and this is ray number 3. All right, so these are all the rays that we have. If an object is outside the focal point, it produces this type of image, an inverted image. It may be bigger or smaller. It sort of depends on where it is. Is it virtual image or is it real image? Does this produce a virtual or a real image? It produces a virtual image. Oh, wait, no, I'm sorry. No, not a virtual. Remember, guys, virtual and real images are different in where they're located. Virtual images are in behind the mirror. Real images are in front of the mirror. Because, listen, if I want to project something onto a screen, I have to have all the light over here. So I would put my screen like right here. If I put it back here, there's nothing going on behind the mirror, right? There's no light rays with our concave mirror. There are no light rays on this side of the mirror. So if I put a screen back here, I'm not seeing anything. I'm going to have to put my screen over here. Kind of like in a telescope, right? A telescope, it takes light from the star or whatever, and it projects it up to the camera, which sits right here. And that's like your screen. You put your camera right here. You don't have to put your camera here. You put a mirror that deflects the light off to your camera. Okay? So my real image for a mirror is going to be on this side. Virtual images will be on this side. They're not real images, they're virtual. They're in that sort of virtual space. All right, it's an inverted image, it's a real image. Now a concave mirror at the focal point will look like this. So an object at the focal point. First of all, before we do this, I want you to think about the mirror equation. 1 over F equals 1 over Q plus 1 over P. If P is equal, or excuse me, if P is equal to F, what is Q? Let's just solve that right quick. Let P equal to F, and then solve for what is Q. And tell me what you find for Q. Let P equal F, and tell me what Q is. So where you have P, you just make that into an F, and then you can solve for Q. Anybody get Q yet for letting P? What is it? What is it? Well, let's look. Anybody else get a value? Okay, close. You're closer. It's not 0 or 1, but y'all are sort of barking up the right tree. What do you actually get to give you 0? You get what? Right, it's undefined because you get 1 over 0, right? And 0 goes into 1 an infinite number of times, and that's why we call it undefined. Look, if I let P equal F, I get 1 over F equals 1 over Q plus 1 over F. And so that's subtracting this from both sides. I get 0 equals 1 over Q. So Q equals 1 over 0. That's equal to infinity, or it's undefined. So the way that works out with our mirror, with our rays, is I draw a ray parallel to the axis, and then through the focal point. I can't draw a ray through the focal point because we're at the focal point, but I can draw one through the center of curvature. This is number 1, rule number 1. Rule number 3, I draw a ray through the center of curvature. Now the way this looks like, I can't, since I'm on the opposite side of, or on this side of the center of curvature, I draw it such that it originates from the center of curvature. So I imagine if you have your straight edge, you would lay down your straight edge such that you would have a straight line up there, and then it would trace back on itself like this. So notice this is rule number 3. And then if I want to, just for giggles, I can do rule number 4 as well. To the center of the mirror, and then it reflects back with the law of reflection. These 3 rays, are they convergent, divergent, or parallel? I know. They're parallel. Yeah, if I was a little more careful in drawing, I would see that they're parallel. So these 3 rays are parallel. That means they're never going to cross if they're parallel. So these are parallel rays which never cross. All right, I'm going to add a little caveat, or not a caveat, but just sort of a further explanation. You might not know what it means right now, but you will in the next one. They never cross in real or virtual space. Where this is real space over here, and this is virtual space over here. They never cross in real or virtual space. They're never going to cross on this side because they're always parallel. And then if I trace them back on this side, they're also never going to cross on that side either. All right, let's look at the next one, and it'll make more sense to you, I think, for the whole virtual space. This one's a little trickier. This is probably the trickiest of all 3 in how we draw these rays. But we still follow the same rules. All right. So the first one, what was the first one? It was through the what? Through the focal point and then parallel to the axis. Remember, that's how we define the focal point. So since I'm inside the focal point, I'm going to draw a ray such that it originates from the focal point and then goes up to the mirror, and then it will go parallel to the axis. So this is rule number one. The next one was parallel to the axis and through the focal point. So it is going to go parallel to the axis like this. Do it in red. Parallel to the axis, and then it traces back through the focal point like that. That's ray number two. Now, convergent, divergent, or parallel these rays are. They're divergent. These rays are never going to cross in real space. They're never going to cross to the left of that mirror. However, they do cross to the right of the mirror. I can trace these rays back. These rays are called virtual rays. And they're just simply where I trace back the reflected ray. I've traced back the reflected ray. Brennan, can you give me just a second? I'll answer your question. So I trace back the reflected ray. And that ray that I trace back is my virtual ray. Brennan? Ray number two is parallel to the axis, and then it goes through the focal point. Anytime this is my optical axis, the dark line. Red line. Oh, you see this little section of red line right here? My incident ray is parallel. So, and the reflected ray, I have two rays here. The incident ray, that's the one coming off the object, and then I have the reflected ray, which is the one reflected off the mirror. And the incident ray is parallel to the axis. The reflected ray, on the other hand, is goes through the focal point. That's a good question. Thank you. We have two rays. The first one, the incident ray, is parallel. Is it raining outside? Yeah. Okay. So now I can do a third ray. I can do a fourth one. I'm just going to do a third one, though. Let's do through the center of curvature. I let my ray originate from the center of curvature. And then it comes up here. And then it reflects back on itself. Like this. And then I trace back my virtual ray. That was kind of tricky, and it's sort of close quarters. So let me just sort of step you through with words. I have a ray that comes through the center of curvature, my incident ray. But because I'm to the right of my center of curvature, I imagine that my ray originates from the center of curvature and then goes on to the mirror. And then it reflects back on itself. When it does so, I see that it's still divergent with these other two rays, and so I trace that reflected ray back. And where it crosses here is where I have my image. So my image is going to look like this. It's upright because where the rays cross are on the top side of the optical axis. And so I draw it just like I had here with the same orientation, except now it's bigger. So this is like your makeup mirror, that when you hold your mirror up close to yourself, then I see myself really big. Right? Y'all see my image big? Yeah, but you look what? Can you see yourselves in it? Right, so you have the first image, which is an upside down, smaller. Oh, it's smaller, right? It looks smaller, but if you hold it up close to you where you're inside the focal point's right here, I'm inside of it, then you look a lot bigger. Okay, so that's a concave mirror inside the focal point, and that one's kind of tricky to draw, but it's useful. So to just sort of recap, we have three types of images that concave mirrors can form. They can form a real inverted image. They can form no image at all. When you're at the focal point, you just sort of look fuzzy. Let's see, Brennan, can you help me with this? Is that okay? So how do you look? Big or small? Can you see yourself? And now I'm going to step back, and at some point you're just sort of going to get fuzzy. Are you fuzzy yet? Yeah, and then if we keep going, then you look what? Upside down. So we transition between those three images. First you look big and upright, then you look just fuzzy, that's no image at all, and then you look inverted and maybe smaller. It's sort of, you can be bigger or smaller. Okay? When you're up close, is that a real or a virtual image? That's a virtual image. Okay? When you're back behind the focal point, outside of the focal point, that's a real image. You sort of have to know that. It's a little tricky with mirrors because you actually can't project. Well, you can project it onto a screen. Oh, never mind. We'll just say that you can project it onto a screen. It's just a little trickier. Okay, now the convex mirror is similar, but we only produce one type of image with a convex mirror. Is this image virtual or upright, do you think? And why? And we know that is it virtual or real? We know that the image is upright, right? Because you can see yourself. And it doesn't matter where you stand. If you stand really close, it's upright. If you stand far away, it's upright. So is the image virtual or real? Why is it virtual? Okay, yeah, maybe that's an okay argument. But we can also think about our image orientation. Is our image upright or is it negative? It's up. Is it upright or is it inverted? It's upright. That means that Q is positive or negative. It's positive. So let's think about our, I'm sorry, no. Let's think about our magnification. It's negative Q over P. I know that this is positive. That means Q must be negative. And since it has to be negative, it must be negative because it has to negate this negative in order to make my magnification positive. P is always positive as far as we're concerned. So that means that I always produce a virtual image. I'll always produce a virtual image with a convex mirror. My rays look similar. I can go parallel to the axis, like this. But now instead of going through the focal point, because my ray is going to reflect off, it's not going to go like this. Instead, what it's going to do is it'll reflect off like this, such that if you traced it back, it would trace back through the focal point. So this is ray number one. Remember the rule for number one was parallel to the axis through the focal point. So what I've done is I've drawn a ray parallel to the optical axis, and then it reflects such that if it goes this way, it traces back through the focal point. I can also, this is my virtual ray as well, so I know that my image will lie somewhere along this ray. The second one is through the focal point and then parallel to the axis. This one's a little tricky. I have to draw it like this, because if I were to trace it forward, it would go through the focal point. Now that's not your virtual ray. The virtual ray is always the reflected ray traced backwards. Now it goes parallel to the axis like this. If I trace it backwards, it goes right there. Now I have enough to draw my image. My image is right there. It's upright. It's smaller, just as I know it should be. It'll always be upright. It will always be smaller. I can do my third rule. What was my third rule? Oh, through the center of curvature. I trace a ray. Oh, this is even trickier. Might want to use a straight edge of some sort. I trace a ray such that if I traced it forward, it would go through the center of curvature, goes in that direction, and then it reflects straight back on itself too. And then if I trace that reflected ray back on itself, then it goes through this point right here. So all three rays will converge there. I can do the fourth ray too. I'll just do it just because the fourth ray comes here and then goes here. And if I trace it back, they all cross at that point. where the image is. Okay? Again, you're not going to have to draw the ray diagrams, but they're useful to help you think about where the images are. If you forget, you can just sort of draw those two primary rays, rule number 1 and rule number 2, and then that'll remind you, oh, okay, a convex mirror, it produces a virtual image, which is behind the mirror. A concave mirror can produce either a virtual or a real image, either an inverted image or an upright image. Said this before, though, upright images are always virtual because of this whole thing right here. If I have an upright image, it has to be virtual because in order to be upright, that means that Q has to be negative. In order for M to be positive, Q has to be negative. Okie dokie? I look sort of zoned out on this. I think we have some clicker questions. I'm going to change this. What kind of mirror? I'm going to change the image here because actually there's no mirror that can produce this image. Um, why can no mirror produce the image as it's drawn here, by the way? Because I have an upright image that is it real or virtual as it's drawn? Is that a real or virtual image? No, remember, real images are on the same side as the object. Because I can put a screen right here and capture the light. So this would be a real image, but it's also upright. So this cannot be the case because I can't have a real upright image. Right? I can only have real inverted images. So that image it's not possible to make that. So let's see. Let's do this. This is my image. There's my object. Tell me what kind of mirror has produced that image. Okay, doing well. Ask your neighbor if you like what they think. I'm going to stop at 58. 58. Okay, good. C is right. It has to be a concave mirror. This is like where you're inside or outside the focal point. You're inside. That means you're inside of the point. You look really big, right? It's like your makeup mirror. So this is a real upright, or excuse me, a virtual upright image. It's bigger, so that means it has to be a concave. Right? It's concave because convex mirrors only produce a smaller image. So it's virtual, upright. First you say it's virtual and upright. Virtual images are always upright. And then a virtual upright image can be produced by any one of the three mirrors, right? So you want to ask yourself about the size. If it was a flat mirror, it would be the same size as the object. If it was a convex mirror, it would be smaller than the object. Because it's bigger than the object, that means that it is a concave mirror. It's virtual, upright, and bigger. That means the magnification is greater than 1. And so this leads you to concave. It has to be a concave mirror. You'll need to know what types of mirrors produce what types of images. Going through your ray diagrams will help you with that. As I said, they're in the homework. If you didn't quite get it today, they're in the homework, and they're in the homework solutions as well. You will have one multiple choice question where you have to pick out the correct or incorrect ray. So you'll need to be familiar with the rays and the rules of how to make them, but you don't have to draw the rays from scratch. All right, which of these will produce a virtual image under particular conditions? Concave, convex, or flat? Which of these is capable of producing a virtual image? All right, I'm going to stop at 45. 45. Okay, good. 1, 2, and 3 is the right answer. Any one of these can produce a virtual image. The concave can produce a virtual image inside, at, or behind the focal point. You be close to the mirror, at the focal point, or far from the mirror for a concave. Inside the focal point. Remember, with our concave mirror, if I get up really close to it, Emma, is that okay if I put you really close? If I get up really close to it, then you look big, okay? If you're far away, then you look inverted. That's a real image, because you can project it onto a screen. The convex mirror, inside, outside, or at the focal point for a convex mirror to produce a virtual image. That's a bit of a trick question because you can't be inside, at, or behind the focal point because you're always on the opposite side of the focal point. So this one always produces virtual images, and this one also always produces virtual images. Doesn't matter where you are. So A is the right answer. I'm going to tell you a joke for the previous one. You want to hear it? Why was the sand wet? Because the seaweed. Okay, let's see. Give me just a minute to think. I think that we are not going to do lenses because this is what I'm thinking. I want to do some of the clicker questions for mirrors, and then on Friday I want to have time to review for our test. And then also on Friday I want to have time for y'all to sort of work together on the take home. So what I'm intending is that we'll do the clicker questions now for mirrors, and then come Friday we'll review all the stuff that's for the test. That's the chapter on rotational kinematics, the chapter on Newton's laws, torques, momentum, energy, all that business, and then this chapter as well, up till just including mirrors, not including any lenses at all. And then on Monday we'll have our test. But at the end of class on Friday, for like the last 20 minutes, I'm just going to go and y'all can sort of work together on your take home. So I would try in the next couple of days to make good progress on your take home. That way you'll sort of know what's going on when y'all sit down. You don't have to participate in that. That's fine. If you just want to skedaddle at 20 minutes, that's fine. But if you want to sort of work together on your take home, then I allow that. Many of you don't know one another, so this will allow a good time for you to come together and just for 20 minutes sort of flesh out your progress on the take home. All right? Any questions about that? Does that seem like an okay plan for you? Yes? Okay. Well, let's do some of the clicker questions for mirrors. An observer at point O is facing a mirror and observes a light source, S. So S is the light source. Where does the observer perceive the mirror image of the source to be located? What position? A, B, C, or D? Where does the observer perceive the image to be located? Let's stop at 55. Oh wait, no, that's not right. The observer views the image. The image in flat mirrors is always exactly opposite the mirror. Now you're saying, well, the mirror doesn't extend down here, but you can see things that are beyond the range of the mirror, right? Like standing in front of your mirror in your bathroom, can you see your feet or your knees maybe? Or somewhere below the mirror, your legs? That would be like this. You can still see objects that lay below the level of the mirror. If you draw your rays, they look like this. Uh, doesn't really matter where the observer is, but if I draw a ray here, y'all will do this next semester. It goes like that, traces back like that, and then I can draw another ray, say at a steeper angle, and where they cross is where the image is. It doesn't matter where your observer is, the image will always be where it is. And it's always going to be exactly opposite the... All right, you stand in front of a mirror. How tall does the mirror have to be so that you can see yourself entirely? If you can see your entire body, how tall does the mirror have to be? Does it have to be the same as your height, less your full height, but more than half your height, less than half your height, or will any size do? And here's some rays showing light from your eyes, or light from your feet rather, that travel up to here, and then light from the top of your head that travel there. So now what size must the mirror be in order for you to see the entire range of your body? Just a second, I'll blank this for just a second. All right, I'm going to stop at 128. All right, the answer here is C. We want to think about how our rays are traced. I think the rays are traced will give you the mirror to be half your height. I get I get a certain distance here, and then I get this distance, which goes to half my midsection. You can imagine it might be better that you have eyes on the top of your head, and then you don't even really have to think about the forehead. In that case, you would have to have a height that bisected your body. Right? That's not terribly important for this class, but just sort of as a point of interest. Yeah. Well, that's the next question. Yeah. So the next question is, let me ask you that question. Does this depend on your distance from the mirror? So what Brennan was asking, what if you have a smaller mirror? Can't you just back away from it and then you'll be able to see more of yourself? Is that true? So does this depend on the distance from the mirror? No, that would say that the distance from the mirror doesn't affect how much of you see in yourself. That if you move further back, then you're not going to see more of yourself. Yes would mean if you move further back, then you will see more of yourself. C depends on the mirror or depends on the person. Maybe if you're really tall, does that matter? Does anybody have a little mirror, like a little compact mirror? No? Oh, y'all use your phones, right? Use your phones? Yeah, okay. I guess it might work with your phone. I'm not sure. I'm going to stop at 1 minute. Okay, the answer here is A, that it doesn't depend on the distance from your mirror. That in fact, if you have a mirror and you move away from it, it doesn't change how much of you see yourself in the mirror. You can try this, go in the bathroom and say, well, my head is right here and my legs are right here, and then back up. and you'll see that you don't change the amount of you that you see in the mirror. It doesn't depend because the rays are still going to trace out exactly the same way, just at different angles. But try it. You can try it with your phone too, maybe, where you take it and you see a certain part of yourself in the mirror of the phone, and then as you pull it away, you still see the same amount of you. I think it'll work in the phone, but I haven't tried it. Right, you would still see the same amount of yourself in the mirror if you could. I mean, if you could still see the light from the mirror. All right, y'all try it. Next time you go in the bathroom, look in the mirror. Now be careful in the bathroom because we usually think that, I think, because we have a vanity in front of us, right? We have that shelf with the sink and stuff on it. And if you back up, then light that's coming from your feet is no longer being blocked by the sink. So you really have to have a mirror that's unobstructed. If you have like a medicine cabinet, it works well because you don't have that vanity right underneath the mirror. All right. You hold a hand mirror 0.5 meters in front of you and look at your reflection in a full-length mirror 1 meter behind you. So this is your hand mirror. It's, yeah, I can't see that. It's 0.5 meters. This distance is 0.5. This distance is 1 meter. I want to know how far in back of the big mirror do you see the image of your face? So your face is over here somewhere. Where is that? How far back do you see the image of your face, your actual face? You can actually, if you have multiple mirrors in your bathroom, right, you can use that to look at different parts. And sometimes you'll get like multiple images. You ever see this where you get tens or hundreds of images in your mirrors? Sometimes my wife and I, like when we're brushing our teeth, we'll get those, and I'll talk to one of the images, and she has to figure out which image I'm talking to. Y'all should try that. It's kind of fun. It, you can do it with practice. All right, we'll stop at 120. Okay, awesome. C is right. It is 1.5 meters. My object is the image in this mirror, which lies zero point 0.5. Oh, wait, no, that's not right. It lies zero point 0.5 meters back here. So you see an image of yourself. The answer is actually 2 meters. You see an image of yourself that's over here in the flat mirror that you're holding. And that's zero point 0.5 meters here. But the image that you see over here is actually 1 plus zero point 0.5 plus zero point 0.5, which is 2 meters. So you have to consider where is the image that's produced in this mirror, 0.5 meters to the right of this mirror, and then this image is in this mirror, which is going to be a full 2 meters behind the mirror. I was about to tell y'all a joke. Glad that I didn't. The answer is 2 meters. You want to set a pile of dry leaves on fire? Which of these mirrors is the best tool? Or you want to burn an ant? You ever do that? Burn an ant? No. Which of these is best to do this? A flat mirror, a concave mirror, or a convex mirror? All right, we'll stop at 35. Okay, so what you want to do is you want to have a mirror that will take rays from the sun and focus them all at a point. You use this with a magnifying glass too sometimes, right? So people more commonly have magnifying glasses. You'll take them outside and you can set fire to things. Ever done that with a magnifying glass? A magnifying glass works very much the same way as one of these mirrors. This is what type is this called? This is concave, right? It caves in. So the answer is B. It's the concave mirror. One time I had my son out, he had a magnifying glass. He was just a little kid. He was like 2 or 3. And we were setting fire to, just like, can I finish my story? We were setting fire to some leaves with the magnifying glass. It was a sunny day. And I was just thinking, gosh, I wonder how hot that really is. And I put my hand underneath the little spot, the bright spot. Have y'all ever done that? It's really hot. It really burned pretty bad. So don't do that. It's actually quite hot, uh, and but it converges all the rays of the sun. Jesse? Okay, you're right. Yeah, magnifying glasses are convex, but a magnifying glass is a converging device, just like a concave mirror. Unfortunately, we're not going to get into the differences in those, but this type of mirror is like the convex lens. They're both converging devices. Convex refers to the geometry, not what it does to the light. Okay, don't sweat that. We're not going to worry about that now. Um, let's do this one, then we'll wrap up. These folks are looking into a mirror. Based on the image, which of these is true about the mirror and the image? So notice these are the people right here, and this is their image. It's an upright image, and it's bigger than they actually are. They look real big. So what type of mirror is it, and what type of image is it? And then we'll make this the last one. Remember, on Friday, we're going to have a review for the exam. If we have more of these, I'm not sure if we do, we'll do them on mirrors. And you're not going to have any lenses on your exam, but you will have mirrors. You'll have a couple questions about mirrors. All right, I'm going to stop at 45. All right, good. It's a concave mirror, and those are virtual images. That's the Hubble Space Telescope, the mirror for the Hubble before it went up. Well, we'll stop there. Y'all have a good day. Remember to